All right, so in this lesson, we're going to talk about Euler's method, which is an approximation or numerical method for solving a differential equation. There are some times where we just can't separate and integrate or solve the differential equation easily, or we just simply don't want to. So we've got options. We can create a slope field, but that involves plotting points, and sometimes we just don't want to even graph a slope field in general. So what's another way that we can approximate the solution for the differential equation if we can't solve it or we just simply don't want to solve it? Well, one method is Euler's method. There's other methods out there. There's the Runge-Kutta method, but this one is the most basic and most straightforward method that we've got, because what it does is it boils everything down to linearization. Now, what is linearization again? It's the idea if you zoom in small enough, everything looks like a line. So we know that for any point on a curve, we have a tangent line, and the slope of the tangent line matches the instantaneous rate of change. We know all that. But what we're going to do is we're going to use that line to help us approximate another point on the curve. Now again, this is only going to be effective if we can zoom in small enough. So what's basically happening is this. We have this curve f of x, and we have this known point, this initial condition of x naught, y naught. Well, what we've got is that we want to be able to approximate another point on the curve. But we can't solve for the differential equation. We don't know what the f of x actually is. We just have its derivative dy dx. So what we're going to do is we're going to use the tangent line to help us out. So again, if we zoom in really close enough, we can find another point on this tangent line because we know that a tangent line, we know its slope, so we can create basically a step size. What I'm going to do here is I'm going to show you that we basically can create a step, a rise over run value, that will allow us to find another point on the curve. Now obviously this point on the tangent line is not exactly the point on the curve, so there is a little bit of error. However, if we can keep on making small step sizes, so if we can make the increment very, very tiny and the window for which we are looking for very, very tiny, we're not going from, let's say, we want to go from x equals 1 to x equals 10. That's a really big distance. But if we want to go from, let's say, x equals 1 to x equals 1.5, that's a lot closer. We can make a small little window and with small little increment step sizes to get where we want with a pretty good approximation. Now, what's happening is you're starting with this x naught, the given initial condition, and you want to go to a specific step size a distance away where the delta x is the change. Some textbooks and teachers will use delta h, so you've got this delta h. It means the same thing, and you use the same idea when you use the limit definition of derivative, where we got the delta x or the delta h, same exact idea. So you've got some distance away, and you want the distance obviously to be close. You don't want to be too far, otherwise we're definitely going to have a massive error issue because it's definitely going to be too far off. And what we're going to do is we're going to keep on using incremental values to get to the point that we want. So it's an iterative method, so it's a numerical method to find or solve a first order differential equation. First order meaning we only have one derivative, dy dx. We're not talking about a second derivative here, okay? And where we don't have ability to either separate, integrate, or solve this problem nicely, or we just simply don't want to, and we just want to approximate. Where we want to approximate a new value. Okay, so what's going to happen is you start off with this initial condition, and you add a step size. Well, that changes the y value as well, because the y value will also be a step size, but it's going to be a step size along the tangent line, so we have to account for the rise over the run. So this is the general formula on how to use Euler's method, and depending on how many steps we need to take to get there, we don't want to make one big step. That's going to give error for definitely. So we want small steps to get to where we're going. Now we're going to have to keep on iterating this over and over again until we get to our desired value. So here's the big idea. We start with the starting given initial condition, and we move in small increments, which is the step size, either delta h or delta x, whatever the book or the problem gives you, at a time in the direction of the tangent line. Again, we're moving along the tangent line to get where we want. Now, some people in some textbooks will use this form where you're going to be plugging into the equation of a line over and over and over again. Again, notice this is y equals mx plus b. It's just kind of written in the opposite form. What we see is here's the b plus the mx. dy dx is representing that slope. And we keep on rewriting the equation of the tangent line over and over and over again. I personally prefer just to keep everything in a table and organized nicely. It's the same exact process, but it keeps everything in order and we don't have to keep on writing the equation of the line until the last minute. So Euler's method using a table, and this is my preferred method of how to solve Euler's method. You have to memorize the table heading. It's not going to be given to you, but you're given x, y, and you're going to create a column for dy dx, and again, you're given that differential equation. So you have this equation, you're going to multiply it by the given step size, they'll give that to you as well, and plus y, which is your current y value. You're going to fill in this table and you're going to keep on filling in each line according to the step size until you get your desired value. So what we're going to do is we're going to walk ourselves through about 2 to 3 examples of how to use this table to use Euler's method to approximate the solution to a differential equation. Let's do it. All right, so for our first question, it says, use Euler's method. Ding, 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 they want us to use it, so there you go. We could try to solve it, or we could use a slope field, but we're going to use the numerical iterative approximation. All right, so we're going to use Euler's method with a step size of 0.1 to approximate y of 0.3 for the initial value problem, dy dx equals x plus y, and given the initial condition of y of 0 equals 1. So because we're using Euler's method, and they told us that, we're going to set up our table. Our table is always the same. We're going to have x, y, dy dx times delta x, and then plus y. So we fill in the chart once we've got it. All right, so now that we've got our table headings, let's see what we're looking for. Well, we know what dy dx is. I'm just going to write that over here so when we need to utilize it, we can plug it in. Let's find out what our delta x is. Well, our delta x is given right here. And delta x is 0.1. It's our step size. Well, what also did they give you? They gave you an initial condition. This initial condition is right here. So right away, I'm going to put that in my table. Here is 0, and here is 1. Always put in your initial condition right away. Well, what's your overall objective? You want to go from 0 to 0.3. This is where you want to end up. So you want to go to 0.3 and you're looking for that y value. You know when x equals 0, y equals 1. I want to know when x equals 0.3, what's the y value? This is your overall question. Now, we're not just going to go from 0 to 0.3 in one big step. We're going to take small steps, which is a good thing, because otherwise if we went from one big step, we'd have a lot of error. But we're going to take small little steps to get there. We're going to go from 0, and we're going to take one step, which is our delta x of 0.1. So 0 plus 0.1 is 0.1. We're going to take another step, and 0.1 plus 0.1 is 0.2. And then finally, we'll take another step, and 0.2 plus 0.1 is 0.3. Notice that each step is a step of 0.1. We want to be small. So again, it's like you're climbing a staircase where the steps are really, really teeny. So we go from 0, we add 0.1, we get 0.1. We add 0.1, we get 0.2. We add 0.1, we get 0.3, which is where we want to stop. So all we've got to do is complete the chart, and we're going to end up with our value that we need. So here's what we do. We have everything we've got going on, so all we got to do is plug it in to our last column and see what we can discover. So we're going to take x, we're going to take y, and we're going to take our delta x, which we know, and we're going to plug it in here to figure out what we've got. So that means we have 0 plus 1 times 0.1, and then plus, and I'll put it in over here. So dy dx, we're going to plug it into 0 plus 1, because here's our x and our y. Our delta x is 0.1. And what is our current y value is what it's asking for. The current y value is 1. So that means when we multiply this together, 1 times 0.1 is 0.1. And then plus 1, we get a value of 1.1. This is now the current y value. So this current y value comes on down. So after walking one step up the staircase, we are now no longer at 1, we're at 1.1. So now we're going to complete the process using these two current x and y values. So when we plug in, we have 0.1 plus 1.1 into my xy value. We're still multiplying it by the same delta x. That's not changing. But now we're going to add it to the current y value. This y represents the current y value in the row. So we say 1.1. So here, this gives us 1.2 times 0.1. Well, when we do that, we're going to move it over. So we've got 0.12 and then plus 1.1. So 0.12 plus 1.1 equals 1.22. So now this is the current y value that's going to now go to the next line. So after going 2 teeny steps, we now have a new current y value. So the first value, we got 1.1 after going a small little step. And now going a next step, we're now at 1.22. These two, this x value and this y value, is going to go into our next value here. And we're going to see what's going to happen after going our last step. So again, after we go a step, we're at 1.1. We go a second step, we're at 1.22. What's the third step is what we're looking for. So let's plug in. We have 0.2 plus 1.22. Again, times our current step size, that will never change. And then plus the current y value, which is 1.22. When we add these two numbers together, we get 1.42 times 0.1. So, and then you add it to 1.22, and you get the final answer of 1.362. Now, this is the new y value that's going to go into here. This is now our next line of 1.362, which is what we wanted. So we really didn't have to go that far to get our final answer. That means y of 0.3 equals 1.362. So we have found our y value without having to solve the differential equation, without having to graph a slope field, and we just use an iterative method, and we filled in our chart accordingly. So again, how do we start? We plugged in our initial condition, we figured out where we wanted to go, we figured out exactly what the step size values were for our first column. So we always have our first column totally complete. And then all we got to do is plug everything in and keep taking our new y value and using it for the next row. Go across, the new y value comes down to the next row, and you arrive at your answer that you're looking for. Not so bad. It's a pretty straightforward method. And if we were able to actually solve the differential equation, we would actually get a very, very close approximation to the given value that we have here because our step size is so small. So let's look at another question.